Okay, well, let's continue on our way with learning about multiplying vectors. In this topic, we're going to learn about the cross product. Now, just as a review, in the last lesson we learned about the dot product, and what the dot product looked at was, let's say we had vector v and w. The dot product, if I were to look at v dot w, tells me what it looks at is the projection of v on w. So if we call this v cos theta, where this is theta, and the dot product multiplies the magnitude of v in the direction of w and w. So it's v cos theta magnitude times omega, or sorry, well, w magnitude. And the result is a scalar. It's a number. Well, similar but different. What the cross product, the idea of a cross product is, let's say we've got two vectors, v and w once again. If I say v cross, actually, for right now it's easier to think about this, w cross v, what that is, and some angle theta between them, this is a vector that is normal to both of them. So imagine, if this is in the xy plane, that there's a vector coming out of the plane that's perpendicular both to v and to w. So a cross product results in a vector, so some normal vector to both of them, and the magnitude of that is the magnitude of v times the magnitude of w times sine of theta. And we'll talk about how to another way of calculating this magnitude and to find the direction of that normal vector. But the cross product is extremely helpful for us to be able to find a vector that's perpendicular to two other vectors. Alright, so here's an example of using the cross product. So let's say we've got two vectors, w and v, and you can imagine that if we continued w out, or constructed this parallelogram, if we wanted to find the area of this parallelogram, well, the area of a parallelogram is base times the height, and if we, given this vector w and this angle theta, this height is going to equal the absolute value, or the magnitude of w, times sine theta. And that's just basic trig. This height here is the same as this height here, and we're just doing right angle trigonometry. Okay, so here's just one application of the magnitude of a cross product. In this case, if you have two vectors, v cross w, the magnitude of that equals the area of a parallelogram defined by v and w. Okay, but this doesn't what we did is we converted it into a scalar. We took the magnitude. So this has nothing to do with the actual normal vector, and we'll get to that soon. So the idea being that when you do this cross product, the result is not just a scalar. It's more than just a magnitude when you take a cross product. You also will get, if we were to get rid of the magnitude, if we're talking about just the cross product, you get magnitude and direction. And the key thing with the direction is that it's going to be perpendicular to both vectors. So this vector here in red is perpendicular to W, and it's perpendicular to V. And how do you find out, how do we kind of intuit the direction of that vector? Well, there's a very popular rule that if you've studied physics, you've probably heard before, and if you've done anything with vectors before, you've probably certainly heard. It's called the right-hand rule, and the idea is if you were to stick your hand, since we're talking about V cross W, and here it's not commutative, so the order matters. You're going to place your right hand on the V. So on the first vector, and you're going to close your fingers toward the second vector. And what we want to do is do that in the smallest angle. So imagine, let's see how well I can draw. You've got your hand. I'll draw it in green. You've got your hand here on V, and then here's your hand, and those are your fingers. And to close, do the right-hand rule. You'd curl your fingers in towards W, and then what you're looking at is the direction of your thumb. And this is kind of, it seems sort of silly, but you'll get to really recognize this later. Your thumb is going to point in the direction of the normal vector. And so here's your, these are your fingers right there. Here's your thumb that's pointing up towards that normal vector. Okay, so key idea being that when we cross two vectors, the resultant is both a magnitude, and the magnitude being V, magnitude of V, magnitude of W sine theta, times some normal vector to both of them. Okay, well, that's the geometric definition we have here. But the question is, how do you find n? And there's an algebraic definition which I'm going to leave to you to do some YouTube searching to watch its original proof and derivation. I'm just going to give you the algebraic definition, which says that if you've got some vector v, which is vi in the I direction, plus v2 in the j, plus v3 in the k, and w, which is w1 in the I, plus w2 in the j, plus w3 in the k, that to find out the I, j, and k component of the cross product, it is v2w3 minus v3w2 I plus this j plus this k. All right, well, that looks kind of hard to memorize, and so there's a very helpful algebraic trick, and it looks like this. If we're doing V cross W, what we write is we're going to do a 3x3 matrix where the top row is I, J, K, and then we're going to put the coefficients of V first, because it's the first vector, and then the coefficients of W. So we're going to have VI, or V1, V2, V3, and W1, W2, W3. And the way this works, we first close up the I column. So we're going to imagine like blocking out this I column, and then we go across this way. So the vector, the kind of highlighted vector that we're going to get is I back. And we multiply across. So it's going to be V2 times W3 minus W2 times V3. I. So V2 minus W3. Oops. Let's write that again. V2 W3 minus W2 V3 I. And now we need to cover up the J. And as we go across, it goes plus, minus, plus, minus. So then it's minus parentheses. So now we're looking at the J column. So we're going to be getting what J is. And now we're going to be looking at the product between I and K. So it's VW times V1 times W3 minus W1 V3 K plus, and now we highlight the K column. And we're now interested in K. So here we're going to have V1 W2 minus W1 V2 J. The first time I remember seeing this, it looks kind of confusing, but if you can see the order in the structure, it's really just a fill in the chart, follow the procedure, and you're going to get the right answer. So it's have confidence with that. So here it is written again, that we've got V cross W. We write our chart, which is the IJs and Ks, coefficients of V, coefficients of W, and then we just make, like we did before, we look at, in this case, we're looking at what goes into the I column. So we get V2 W3, W2 V3. And then once you get the I component, then we look at J, and remember it's going to be a minus, and then V1 times W3, W1 times V3. They include a plus and then switch the order of operations, but I like to keep it as minus and then going down the diagonal. So V1 W3 minus W1 V3, and you get the same thing. Okay, and then we look at the K term. So for the K term, we're getting our K value, and then we just go across. So V1 W2 minus W1 V2. Alright, so there's 2 times of looking at that, and we'll practice that throughout the rest of this video. Okay, so let's do some examples. It says find V cross V. Well, imagine that. We've got V crossed with V. What's the angle between them? Well, the angle between them is 0. So V cross V, anytime you have a vector crossed with itself, you're going to get the magnitude of V times the magnitude of V times sine theta, and this is a magnitude, times the vector normal to them. Well, we can stop right here because we know that sine theta, when theta is 0, that this equals 0. So this whole thing is 0. So V cross V, or any vector crossing itself, gets you 0 back. Alright, what about IJ? Well, let's first do IJ. We've got, those are both unit vectors, so we've got our unit vector I and our unit vector J. So here's I and J. And if we start with I, put your right hand on this axis, and I would actually put your right hand there, and then curl your fingers toward, you want to curl your fingers toward the J, so in that direction. And when you do that, your thumb should be pointing out of the page. So your thumb should be pointing, it's kind of hard to draw that, but out of the page, sort of out of the computer screen, and that's your normal vector. So your normal vector would be k. And because we're dealing with 3 dimensions, we call out of the page, so coming out of the screen or out of the page, we write that as a vector like this. So imagine that like an arrow with an arrow tip. And then into the page, or into the computer screen, we write like this. So for ji, we've got vector j and vector I. So if you start with your right hand on j and you want to curl your fingers in the direction of I, what is required is that your thumb is going to point into the page. So your thumb represents the vector j cross I. So we have j cross I equals negative k, whereas I cross j equals k. So clearly order matters. All right, so now let's do a cross product with some numbers. We've got v and w. So, and we want to find the cross product of v and w. So v cross w. So that we set up our chart. We've got I, j, k, and v is 2, 1, negative 2. That's their respective coefficients. And w is 3. The j value is 0, and k is 1. So to find out, when we're doing v cross w, it's going to equal 2 times 0 minus 1 times, oops, I'm looking at the wrong ones. For I, we're looking this way. So it's 1 times 1 minus negative 2 times 0 I minus, now we're going to be looking at the j term, so we're going to be looking at this and this. So minus 2 times 1 minus 3 times negative 2 j plus, now we're looking at our k values, 2 times 0 plus 3 times 1 k. So simplifying this, we have 1I minus 8j plus 3k. And that is v cross w. Then it says, check that the cross product is perpendicular to both v and w. Well, to check that, let's just review our dot product. So we know that if they are in fact perpendicular, that v cross w dot v, if they're perpendicular, should equal 0. So let's look at that. Here's v dot w, and here's v. So, sorry, that yellow is v. This here is v cross w. So v cross w, this, dot v, this, will equal, you just multiply their coefficients. So 2 times 1 plus 1 times negative 8 plus negative 2 times 3. So I caught a mistake. This here should have been a minus, which would have made this minus 3, which would have made this a minus 3. And now it works out, because now we get 2 minus 8 plus 6, which equals 0. So that confirms that V cross W and V are perpendicular. And now let's look at V cross W dot W. So now we're looking at that vector being crossed over here with V cross W. So this is going to result in 3 times 1. There's no J term, so plus 0 times negative 8 plus 1 times negative 3, and this equals 0. So the fact that both V cross W dotted with V and dotted with W both resulted in values of 0 confirms that they are in fact perpendicular, which is what we would expect given our definition of cross product. So here are some rules of the cross product. Take a second to look at them. The first one suggests that while the process is not commutative, it's close to commutative. That W cross V is the same as negative times V cross W. And if we have a scalar being multiplied by V, so lambda V cross W, that the position of the scalar doesn't matter. We can cross V and W and then multiply by lambda, or we can multiply W by lambda crossed with V, and we get the same thing back. So lambda is commutative. And the last thing is that the cross product is, in fact, you can distribute across the cross product. So distributive property of cross product applies. All right, so let's get into some problems now. This is in the last video with the dot products. We were looking at how we could use the dot product to find an equation for a plane, and what we recognized with the dot product, or the dot product kind of let us see that if you have some point and a normal vector, then you can write an equation for the plane. And the equation for this plane, as a reminder, given a normal vector to the plane and a point on the plane, the equation for the plane would be A x minus x naught plus B y minus y naught plus C z minus z naught equals 0. And that idea came from that the normal vector crossed with a point on the plane and another point on the plane, a line on the plane, a vector on the plane. So if we had a vector on the plane and a normal vector and we dotted them, they would be 0 since they're perpendicular. But now what we want to do is we want to use this idea and incorporate what we've just learned about cross product and the fact that cross product can give us that normal vector. So the idea being, imagine if we've got 3 points. What you can do is get an equation for this displacement vector. So we could call this, displacement 1, and this displacement vector, displacement 2. And if we crossed D1 cross D2, what we're going to get is and these, we're looking for a normal vector to the plane determined by these 3 points. So if we cross these two vectors, what we're going to get is a normal vector to both of those displacement vectors. So that normal vector that we got here, this would be the vector that's normal to the plane. So now, given 3 points, I can get 2 vectors, cross them, and get the normal vector. And now that we have that, using what we knew before, we can get equation for a plane. And that's pretty cool. It's a pretty cool application of both the dot and the cross product. So let's see an example of that. Here are our points P, Q, and R. And let's sort of let P be our home point. So from P to Q, what we're doing is we have 2I plus J minus 3K. So what I'm doing there is just looking at, from 1 to 3 is 2, from 3 to 4 is 1, 0 to negative 3 is negative 3, and PR equals, well, 2I plus 3J plus 2K. All right, so now I've got 2 vectors coming from the same point, so from P to Q and from P to R. And so to find a normal vector to both of these vectors, which will thus be a normal vector to the plane, my normal vector equals, my normal vector equals PQ cross PR. So we have I, J, K, 2, 1, negative 3, writing the coefficients, 2, 3, 2. And for our I value, we're going to get 1 times 2. Let's do this in another color. 1 times 2 minus 3 times negative 3. I minus 2 times 2 minus 2 times negative 3 J plus 2 times 3 plus 2 times 1 K. And if we simplify this, we have 11I minus 8J plus 8K. And I think I've done this right. It's possible I made a mistake, but I think that's our normal vector. And now that we have a normal vector, we actually have 3 points. We've got this point, and this point. We just need to choose one of them. Let's choose point P, just because that's our first point. So we're going to use that point and this normal vector to get an equation for the plane. So the equation for the plane that's equation. The equation for the plane is going to be 11, that's that coefficient, times x minus 1, the 1 coming from there, minus 8, y minus 3, 3 coming from there, the 8 coming from here, and then plus 8, z minus 0 equals 0. And there's an equation for the plane, and we got that by finding 2 vectors, crossing them, the cross of them equals the normal vector, and then using what we knew before about having a normal vector and some point, which gives us an equation for a plane. All right, this next question continues to look at the idea of normal lines and finding equations for the plane. In truth, this took me a little bit of time to think about before I was ready to answer it on my own. It may jump out at you quicker. But it says find, well, it could jump out at you, just here's the answer. But to develop that answer on your own, it says find the equation of a plane through the origin. So going through the origin, we know that our plane contains the point 0, 0, 0. So find an equation for the plane through the origin perpendicular to this plane and perpendicular to this plane. Well, if our plane, and let's call this plane 1, just to name it. So if plane 1 is perpendicular to x minus y plus z equals 2, then plane 1 must be parallel to the normal line to this plane, because the opposite of perpendicularness is being parallel. So plane 1 must be parallel to I minus j plus k. Similarly, plane 1 must also be parallel to the line that's perpendicular to the plane which it's perpendicular to. Same kind of order of thinking. So plane 1 must be parallel to 2i minus 9j plus 8k. All right, well, so plane 1 is parallel. It's parallel to this line. It's parallel to this, instead of line, we should say vector. So plane 1 is parallel to this vector and parallel to this vector. So if it's parallel to both of those vectors, then plane 1 will be perpendicular to the normal line, where our normal line is going to equal P1, sorry, not P1, where the normal line is going to be the cross product of these two. So let's just take a minute here to really sort of wrap our head around that. The idea being, our plane 1 is perpendicular to this plane, which means that it's parallel to the line normal to this plane. So plane 1 is parallel to I minus j plus k, which we got from these coefficients, and it also, plane 1 must be parallel to 2i minus 9j plus 8k, which we got from these coefficients. This here is the line that's normal to our plane here. So if we were to cross these two vectors, this vector and this vector, if we crossed them, what we're going to get is the normal line to plane 1. Because if plane 1 is parallel to both the first and the second, it will also be perpendicular to the line that both of those are perpendicular to. So okay, now we need to do a little bit of the work. So our normal line equals I, j, k. Now they're coefficients. So 1 minus 1, 1, 2 minus 9, 8, and hopefully you're getting familiar with this now. So our I term is negative 8 minus 9 I minus 8 minus 2j plus minus 9 minus 2k. And if we simplify this, this is just I minus 6j minus 7k, and that's our normal vector to plane 1, which contains the origin. So now we can get our equation. Our equation is the coefficients from our normal line and our point 0, 0, 0. So it's 1 times x minus 0 minus 6 times y minus 0 minus 7 times z minus 0
equals 0. And if we simplify that, it's just x minus 6y minus 7z equals 0. That's a great problem, and I really sort of challenge you to try to get either with demos, like getting a bunch of paper to represent planes, but really try to visualize this idea of a bunch of perpendicular lines and parallel lines and how we can get new normal lines. It's a bit of a brain teaser, but the more you can visualize what's happening spatially, the easier you will, of course, understand the mechanics that's going on. All right, so let's in the remaining part of this video just do some problems so you're familiar with what types of work you might be asked to do. It says find the vector representing the area of triangle ABC, oriented so that it faces upward. So let's just think about this for a second. If we have, I know that this is in three-dimensional space, but let's just put it in two-dimensional space for a second. Going back to the original part of the video, if we think about AB and AC and creating a parallelogram, we know that AB cross AC would equal this whole area. Well, the magnitude of that would equal the whole area. So if we just divide this by 2, this will equal the area of the triangle. The area of the triangle, which is what we're looking for. So now we just need to find those vectors. So AB, so from A to B equals 2I minus J minus K, and AC equals I minus J plus 0K. So AB cross AC is going to equal I, J, K, 2, negative 1, negative 1, 1, negative 1, 0. So if we now do what we know about cross products, if we cover the I, we're going to get negative 1 times 0 minus negative 1 times negative 1, so just 1, and that's I. Minus 2 times 0 minus 1 times negative 1, so minus minus 1 J. And then we have plus 2 times negative 1 minus 1 times negative 1 K. That's a little bit messy, but if we, right, and then this is all divided by 2. So then what we get is negative 1 over 2I minus 1 over 2J minus 1 over 2K. And then it says oriented so that it faces, and this is our vector that represents the area of the triangle. And if we found the magnitude, that would be the area. But this vector represents the area. It's a vector pointing in a direction perpendicular to the plane that triangle is on, and the magnitude of that vector is the area of the triangle. The only thing is that it says that it wants it facing upward, and since these are all negative, coefficients that's facing downward. So our vector or our area vector will equal 1/2 I plus 1/2 j plus 1/2 k. We're just finding the negative. This is just negative v. And that all came from the idea of that a triangle equals 1/2 the area of the parallelogram, where the area of a parallelogram is the magnitude of v cross w. So v w, so the magnitude of v cross w equals the area. Now let's do an example where we find the area of a parallelogram. This is actually, I think, easier, much significantly easier than that problem we just did with a triangle. So if the edges are, v and w, so same thing, we're just going to do v cross w, and that equals I, j, k, 2, 1, -3, 1, 3, 2. And pause this video and see if you can now do this cross product on your own. You've seen it a bunch of times. So press pause and then I'll do it. Okay, well this equals 2 minus 9 I minus 4 minus 3 j plus 6 minus 1 k, which simplifies to 11I minus 7j plus 5k, and that's v cross w. And this is our area vector. But if I want to just know what the area is, the magnitude, so the magnitude of this area is the magnitude of this vector, which equals the square root of 11 squared minus 7, so plus minus 7 squared plus 5 squared, which is 121 plus 49 plus 25. I don't know if this works out nicely. So we get the square root of, I think, 195. So that's the area of that parallelogram, and we use the magnitude of the cross product to find that. All right, so I think the last idea, and we'll do one or two more examples afterwards, is a problem that incorporates both the cross product and the dot product. So it says, first of all, a parallelepiped is kind of like a three-dimensional parallelogram. So the base is a parallelogram, and then the height comes off as a parallelogram. So there's no right angles here. So we know that the base of the parallelepiped, which is going to be a parallelogram, is just the magnitude of b cross c. B cross c results in a normal vector that is going to be a right angle to C and to B. And if we think about that, the angle between B cross C, and so we've got B cross C, and then angle, or sorry, A, and there's an angle between them. If we think about the height of our if we think about the height of our parallelepiped, so really, what is this height here? The height is A cosine theta. Because if we were to, do A cosine theta, what that's going to do is go and look at, if we draw this right triangle here, A cosine theta is exactly this height right here. So if we multiply B cross C, the magnitude of that, times, or rather dot A, and dot A, well, the reason why I'm saying dot A, because if we dot A, what that equals is B cross C magnitude, and when we dot it with A, that equals, that's the same thing as doing times A cos theta. And by dotting it, we don't really need this magnitude anymore, because when we dot our B cross C vector, so B cross C dotted with A, this is going to result in a scalar, and that scalar is the volume. So what we get is B cross C times the magnitude of A cos theta. So in other words, this equals magnitude of B cross C times the magnitude of A times the angle between them. Let's take a second and even extend this a little bit further. So the idea is, when we take B cross C and dot it with A, well, B cross C, using what we know about B cross C, we're going to get B2 C3 minus C2 B3 in the I direction. That's that. Minus, well, minus B1 C3 minus C1 B3 in the J direction, and that's from those. That's from doing this. And then plus B1 C2 minus C1 B2 in the K direction. But when we dot this with A, so dotting all of this with A, which is A1I plus A2J plus A3K, when we dot that with our vector A, what we're going to get is A1 times B2C3 minus C2B3. And if we distributed this negative sign, so plus negative B1C3 plus C1B3 times A2, so multiplying their like components, plus B1C2 minus C1B2 times A3. And this is the volume, and here's the actual expression for it. And the idea is we can use the matrix here to generate that. So the idea is if we use the absolute value of the determinant, so the determinant being the value of, I don't know how familiar you are with matrices, so the absolute value of this of the value of this quantity, and let me just start a new page. That quantity we find using the same way we were doing the cross product. And the study of linear algebra and matrices definitely would help here. But this is B cross C dot A. So the idea being, we're going to fix A1 and we multiply it by B2 minus C B2 C3 minus C2 B3 minus, now we're going to fix A2, so A2 times B1 C3 minus C1 B3, and then plus, and then we're going to fix A3, so plus A3 times B1 C2 minus C1 B2. And this, if we went back a slide, is the exact same thing written slightly different that will find us the volume of our parallel pipette. But more important than memorizing this equation is trying to recognize how we were able to use both the cross product and the dot product in a way to express the volume. And so you really want to understand, not just memorize this equation, but where does this come from? So you should be expected to explain that after watching this video. Alright, so let's just do one problem. We're going to do problem 12, and this will finish off our discussion of cross products. It says, given these points, let's find a plane that contains all of those points. So let's find a vector first. Let's have this be like our holding point. We'll call this, A, B, C. So vector AB is negative I plus J plus 0K, and AC equals negative I plus 0J plus K. So we need to find a vector that's normal to the plane, so that's normal to both of these vectors. So we're going to do AB cross AC, and that equals IJK, negative 1, 1, 0, negative 1, 0, 1. And so we've done this a bunch now. So what we get, AB cross AC, which is going to equal our normal vector, equals, so looking here, we get 1I, and now we're looking here, so minus 1 J, and now we're looking here, plus 0 minus 1 K. So this simplifies really nicely to just I plus J plus K. What a very sweet little vector to use. So this is our normal vector, and we can choose any one of these points. So let's just choose the first point, 1, 0, 0. So the equation for our line will be, using these coefficients, 1, 1, 1 will be 1 times x minus 1, where that's the 1, plus 1 coming from there, times y minus 0, plus 1 coming from that coefficient, times z minus 0 equals 0. So simplifying, x plus y plus z equals 0. Alrighty, so that's our little lesson on cross products. Hope it was enjoyable.